Gillis. Following today's presentation, a recording will be available to you on our contractor resources and HVACR training pages on our website at climate.emerson.com. In addition, we will be providing you with our certificate of course completion following the event via email. Our session will now begin. Don?
Thank you, Kara. Welcome, everyone. Thanks for joining us today. I'm Don Gillis. I'm going to be walking you through. Today is the first of many training courses we're going to have every day for you, the WebEx, at the same time. A little bit about me. I work in educational services at Emerson. I've been with the company just under 3 years. I've been in the industry approximately 27 years or so, at all different levels. I am a licensed journeyman and obviously have my EPA and several other things. I sit on a couple boards and travel immensely through the year with doing all kinds of trainings. We offer trainings from 4 hours to 5 days, and we cover all of North America. So today we're going to start with the refrigerant cycle, and we're going to go with the basics just to get a good foundation of future classes, okay? But before I start, I want to talk about these apps that we have. Emerson has a lot of apps. These are 3 that I'm going to encourage you to download after the session. If you can do it before the session, you're more than welcome to. I'm going to touch a little bit on the one to the right, the PT PRO, which is nothing more than a digital PT chart. The one in the center is Copeland Mobile. That's our bread and butter, our best app. It has a lot of information on it. I'm going to do a presentation, I think, in about 2 weeks on that app alone, or several apps, but that's going to be primarily talked about. And then on the left, we have AE bulletins. In the classroom, I normally describe that as kind of like our Google, if you will. You can put, filter dryer in there in the search bar, and it comes up and tells you. That is written by engineers, and it's how we feel about every one of those components or applications. It is kind of like the Bible for us, if you will, okay? So let's get started with the refrigerant cycle. Some of you, like I said, this might be just a refresher, maybe all of you, I don't know. I've been told there's a lot of people that are just starting in the industry, so hopefully you'll get something out of this, okay? So starting with the left, refrigeration is the transfer of heat. We don't really make anything cold. We move heat, don't we? We remove heat and put it somewhere else where we don't want it. And air conditioning is refrigeration at just a higher temperature. And we have a higher temperature, we have a higher pressure, okay? And remember this throughout the course today. High pressure follows low pressure, and hot always goes to cold. In a very layman's terms, okay? That is the basic foundation of the physics of what we do in our industry. And then we have different refrigerants are used in refrigeration. 404A, 134A, and all kinds of refrigerants now coming on the scene. CO2 for your supermarket folks and natural refrigerants and what have you. But at the end of the day, everything we do in the industry has these 4 basic components, okay? We have the evaporator, the condenser, okay, the expansion valve, and the compressor, okay? I'm going to talk a little bit about each one of those briefly. So here is the 4 basic system components, okay? And when I was trained years ago, my first class, I was trained, I'm sure most of you, or some of you have anyways, have been taught the baseball diamond way, and I'll explain that a little bit later. But let's start with the evaporator here, okay? The evaporator, first of all, we name all these components for what they do, as silly as that sounds, right? The evaporator evaporates, the compressor compresses, and so on and so forth. But they all do one thing and even 2 things. Most of them do, and a few things. And we'll talk a little bit about that. I'm going to start with the evaporator. So when we talk about the evaporator, we're talking about the evaporator is located inside the conditioned space, and it goes from low pressure liquid to low pressure vapor. It also absorbs the heat that's coming through the system, all right? Think of the coil, again, as a big empty sponge, and the colder it is, the more saturation in there, we can absorb more heat, okay? So that's what we do. Again, staying with the theme that hot goes to cold. It absorbs that heat, and it moves it on down the line here to our compressor. What does the compressor do? Well, obviously, it compresses, okay? And there's many different types of compressors. There's rotary, recip, scroll, centrifugal, all kinds of compressors, but they all compress vapor refrigerant, okay? We don't want to get any liquid refrigerant in our compressor, or we would hear those crunchy sounds, okay? So we'll talk a little bit more about that as we move along, okay? So it compresses low pressure vapor into high pressure vapor. It is the lowest point of pressure in the system. It's also the highest point of pressure in the system when it leaves, okay? So we're raising that pressure and raising that temperature to literally chase that refrigerant all around the system. That's what it does. It is a vapor pump, okay? Now, it rejects heat. It desuperheats, okay? And it rejects the superheat, the heat of mechanical heat, the heat from the load, the heat of compression. Whatever heat it picked up across the motor, it's rejecting that, okay? It's desuperheating. Let's go to the condenser. The condenser, it just simply condenses high pressure vapor into high pressure liquid. It desuperheats it, and it rejects the heat from the load, the heat of compression, and the superheat, okay? And then we have the metering device, okay? The metering device does two things. It controls the amount of refrigerant going to the evaporator, first of all, but more importantly, it causes a pressure drop. So what it does is it causes a pressure drop. So in other words, this compressor, like I said earlier, I kind of misspoke and got ahead of myself, but this compressor is compressing, okay, and it's building up pressure up against this metering device. In this case, it's the expansion valve, thermostatic expansion valve, okay, and it has to be there, okay, for this pump to be able to build up pressure. In other words, if you had an air pump that you were filling up your tire with, if you cut the hose off of it, the valve that you put on the Schrader valve, and it was just blowing outside, you would never be able to build up pressure. That pump would just keep running and running. So this is our pressure drop, okay? So it causes a pressure drop. And like I said, it controls the amount of refrigerant going to the evaporator, all right? And what I meant by this ball diamond, the way I was trained years ago, my instructor's name was Kevin, and he pointed out to all of us in very simple terms, we were all green when we were starting. He said, think of the compressor as home plate. I want you to think of the evaporator as first base. I want you to think as the condenser as third base. And then last but not least, the metering device will be second base. And if you were to draw a line from home to second base, what you would find is everything above that line is high pressure, north of that line, okay? So this, between the home plate and second base, everything above that is high pressure. Whether it's liquid or whether it's vapor, it's high pressure, okay? Everything below that line is going to be low pressure, okay? Everything, whether it's liquid or whether it's vapor, again. And last but not least, if you were to draw a line between third base and first base, you would have vapor below that, and you would have liquid above that. Again, whether it was high pressure or low pressure, all right? So everything above third and first base. And I like those analogies, especially with people that you're training when you go out in the field. You can think about that. We all kind of can wrap our head around sports analogy of some sort. And you can do it with anything. You can do it with bowling. You can do it. This is just happened to be the way that I was originally trained. If you were to go online and Google it, you would pull a lot of these pictures out, just putting HVAC on there, okay? So a refrigerant is nothing more than a chemical compound which is capable of repeatedly changing its state from liquid to vapor back to liquid while maintaining its chemical stability. What it's saying there is we don't just pluck these refrigerants out of the sky and use them. I mean, all liquids are refrigerant, okay? All fluids are technically a refrigerant. For example, water is a refrigerant. It has a number, R718. Gasoline is a refrigerant, but obviously it's flammable. So they have to hit a certain criteria, okay? They have to be stable and not break down. In a perfect world, which it's not, if we don't touch this system, in a perfect world, that refrigerant should stay good all the way through its life. But it's not a perfect world, okay? Unlike motor oil, where we know we're gonna change the oil every 3,000 or 5,000 miles, refrigerant systems don't do that. It's not until someone like myself walks up onto a system and puts my 6-foot hoses on it and contaminates something that we start to have problems, right? And if you don't believe me, I'll talk a little more about how to install and some of the factors that cause havoc on the system. And last but not least, we'll have relatively high latent heat. And latent heat simply means hidden heat, okay? And we're going to talk about where we would find latent heat. Latent heat is nothing more than hidden heat. And then it has to have a low boiling temperature, and that's why water necessarily isn't a good refrigerant. Now, we use water in chillers and boilers and that thing because it does transfer heat well. It just doesn't, it's not a good refrigerant, right? So I'm sure a lot of you have seen this chart before. I know the first school, again, that I went to, this chart, and it's a piece cut out of a lot larger chart. So you would have another line here that would be changing ice to water, okay? And this chart is based on atmospheric pressure, which we know is 14.7, unless you're in Denver, Colorado, and they'll let you know right away that it's not 14.7. And I went back the next time with some high altitude PT charts. But for this conversation, it's going to be 14.7. And what this chart is telling us is the BTUs equals the amount of heat energy to raise 1 pound of water at 1 degree Fahrenheit at sea level, okay? That's all it's telling you there, okay? It's also telling you the sensible versus latent. Remember, I said latent heat is changing state but not changing temperature. It's a hidden heat, okay? Sensible heat is something you can sense. We can touch something, we can sense it. A thermostat senses a temperature difference in the set point, and it turns on, right? So that's the difference between the two. Now, we have water, all the ice is melted. I'll kind of walk you through this here. The ice is all melted, and as the water gets warmer, okay, it gets up to the boiling point at atmospheric pressure, which again is 14.7. We start to boil the water, okay? And it's going to keep boiling no matter how hot you turn this up. As long as there's liquid in that pan, if you will, on your stove, it's going to say 212. That's considered latent heat. So we're changing temperature, but we're not changing, temperature, or not changing temperature, but we're changing the stage that it's in, the state that it's in. So all the way from 212 to 212 at the end, it's not until that very last drop of liquid goes out of the pan and goes to 213 that it will go to change the temperature. And that 1 degree, that 213, or that 1 degree over 212, when it turns to a vapor, is sensible heat, but it's also superheat. It's our industry. That is the evaporator. That's also the condenser going back from the vapor to a liquid, okay? And that's how that works. So let's talk about refrigerant piping a little bit, okay? The two biggest reasons we have piping for what size, for what they do, and I never understood this when I first started, and some of you may have on-job training or went to school, but the two biggest reasons we size the pipe for what we do, we have to have it large enough to bring the volume to cool the compressor down, and we have to have it small enough to have enough velocity to drive the oil back to the compressor. Those are the two biggest factors. So if you ever wondered when you pulled that installation manual out, what it's telling you, how many feet you got to change, at a certain feet you might have to change the size of your refrigerant line, that's why. That's what the manufacturer, the person that designed that equipment, the OEM, is telling you, okay? Now, a little thing about piping is it's referred to as ACR piping, okay, air conditioning refrigerant piping. It's not plumbing piping, and the reason it's not considered plumbing piping like out of a hardware store is it's dehydrated. It's also seamless. You can get it in soft or hard copper, and we measure refrigerant copper by the OD. And just to show you how important this refrigerant line is, for example, if we were to use an old line set going into a system and this liquid line, for example, was too small, you know what would happen there, okay? It would act almost like a metering device, and it would build up pressure and go back to the compressor and run hotter. That's going to take it out of the envelope. It's also going to raise the compression ratio. And compression ratio is the #1 reason that compressors fail out there, okay? The #1 reason, it's overheat, all right? I slipped this in here real quick. It wasn't really part of this, but I try to help people out when I travel just to try to bring more value, not only to their companies, but themselves. And if you ever see an enthalpy chart and you start getting into management or you get 10, 5 years, whatever, in your career, when you look at an enthalpy chart, this is an enthalpy chart. And inside this thumbprint, if you will, is our two-phase area of the system. So in other words, we have liquid and vapor inside this thumbprint, okay? Over here, when you see this line going up here on this enthalpy chart, all it's really saying is, these are actually in there already, all it's really telling you is this is what's happening to the compressor. On the left-hand side is your pressure, on the bottom is your temperature. When it comes across here, it's referring to the condenser. If this wasn't wrote here, just remember it's your condenser, and it's where we're rejecting that heat out that we talked about earlier. When we hit 0.3 there and go down vertically, we're talking about our metering device, all right? So we're coming back here, going into this, we're coming across, this is where we're absorbing that heat, this is our evaporator, okay? So on this side is our liquid side, and this side is on our vapor side. And just a little side note here, if you ever look at a PT chart and it says bubble or dew point, we're looking at our dew point on the vapor side, and they're referring to the bubble point on the liquid side. And the way I look at that is, remember sub-bub, okay, and su-dew, okay? That's the way I recall it. So let's talk about refrigerant air conditioning installation and service best practice. Now, most of you know this. I'm sure all of you know this, but it's important to do the installation properly, because what we've found is, and what I found, and I didn't know when I first started my career, what we do today affects this compressor 5 years from now. So if we don't do a good vacuum down to our Micron gauges, that water inside that system, or that moisture, is acidic, and it'll show its ugly head 5 years from now. So when I go out to the system and I pull up to Mrs. Jones' house and I tell her she's got a bad compressor, the comment's going to be from Mr. Jones, they just don't make it like they used to. Well, it's not really that. What we didn't know, and what I didn't know, was it was something on the initial installation. And I'll tell you how important it is to me, that's a great observation, is how many of you have had someone show up at your house in the last 5 years, or 10 years, let's say 10 years, and showed up to fix your refrigerator, okay? How many in the last 5 years? Probably not many, if any, okay? And my point is those refrigerators are being assembled inside a factory in a controlled environment. They're using the proper nitrogen while they're brazing, okay? They're keeping everything clean. That's why you can go through the whole life of the refrigerator and more than likely never have it serviced. That's the purpose of it, okay? Recapping on what we just talked about, we're going to select the correct size of the piping and the type of tubing. We talked about ACR. We're also going to cut with the proper tools. We're going to make sure we deburr that. If you don't deburr properly, or for some reason that gets into the copper gets into the system, it may restrict a TXV. It may get stuck in the liquid line filter dryer. It's going to depend on where you're making that braze at. It could also fall on the windings of the motor and cause a short down the road, and you don't know down the road what caused that. We see flux more and more in air conditioning. It used to be more of a plumber's thing, but we want to clean and flux as needed. Okay, this is where I typically ask the class who uses flux. There's no shame in that, because a lot of our connections on our compressors now are a copper-clad steel, so you have to use the flux to get a good heat joint on there. And then ensure proper fit and fasten as required. We have to select the proper heat source, and I'm going to stop right there. I'm comfortable with settling oxygen. I do have a turbo torch. What I can tell you about turbo torches, and I know that's a brand name, is be very, very careful, because what I noticed when turbo torches came out, I was actually doing the warranties as a service manager, and what I noticed is a lot more pieces getting damaged. For example, TXVs, service ports. So the longer you stay on something, the more likely you're going to damage something if it's not protected, or even if it is protected. I like my settling oxygen. I can get on and get off, and then use a good filler material here. Last but not least, my favorite one. I always tell everybody in class, I'm not trying to sell you anything, but it says here, purge with inert gas during the brazing process. I usually ask everyone at this point who brazes with nitrogen as they're brazing. And usually I get a mix of 50-50 or 60-40, somewhere thereabouts. But the importance of purging while you're brazing is we're trying to remove that oxidation inside the system. For example, here, this is a test we ran in the lab in Sydney, Ohio at the Copeland plant, Emerson plant. On the left-hand side, we didn't use nitrogen, okay? On the right-hand side, we did use nitrogen. You can see all the flakes here that came out of this. And what I didn't know before I started here was all the things that you see on the outside of the line are going on the inside. Even though I was using nitrogen, I didn't realize how bad it was, okay? I remember years ago being in a shop, and the owner of the company said, hey, come in tomorrow. We're going to get certified for this new refrigerant coming out. And we all looked at each other, and it's a new refrigerant. It's called Puron. It's 410A. And I remember the next morning, the guy giving us the, 10 slides, if you will, and then took a test. We had to take a test on top of our 608 for just high-pressure 410A. And I remember the guys graveling in the back of the room, the older guys, and they were all saying, oh, that's a bunch of bull and this and that. They told us that with R22, and it was nothing. But what they didn't realize, and these are the people I was learning from, and they're very smart guys, what they didn't realize, though, is we changed to POE oil. And POE oil changed the world. POE oil, because of the way it's made, it is like a flush, if you will, okay? It will make something like this look like that, okay? When mineral oil's around, things would fall down and get into a corner to hide themselves, never be seen again. But with POE oil, it picks it up and moves it on down the line, okay? I always use like a snow globe is one of the best analogies I have ever heard. You take a snow globe and you shake that snow globe, and those flakes are hitting the ground. When they hit the ground, that's mineral oil. But as the flakes come down, if it's POE oil, it picks those flakes up mid-air and takes them on down the road, okay? Standing pressure test. Now, this is going to depend on where you're at and what your codes are for the most part, but I'm going to say nominally the piping pressure should be tested somewhere around 1.5 times the working pressure of that line. You always want to see the nameplate, always, okay? Photograph of the manufacturer's nameplate must be submitted to verify working pressures in some jurisdictions, not necessarily all of them. This just happens to be one jurisdiction. I think I pulled this one when I was giving a class recently out in California. But again, never, never, ever go above the pressure nameplate. Now, the thing I want to tell you is if something's really old equipment and it doesn't have a nameplate, keep in mind refrigerants didn't go as high as pressure as they do today, okay? So you never want to go over somewhere around 100 pounds. Be very, very careful with that. And then we've got leak detection. Once we pressurize it, we want to check for leaks, right? So we've got good old tried and true bubbles. We also have electronic, the sniffers, and then we have ultrasonic. I always preferred to have two. Most everybody has bubbles on their truck. Hopefully you've got another source, a electronic, because bubbles don't always fit the bill. For example, if you have a leak in an evaporator, you might have to get the sniffer out and stick it in there, okay? Evacuation. Evacuation, I know people say you don't actually remove water from a system by evacuating. You're getting non-condensables, but you're removing moisture. You're just changing the pressure inside there. It's not 14.7 where water boils at 212 anymore. Okay, we're removing the moisture by vapor, aren't we? We're picking up the non-condensables, okay? A little rule of thumb on using vacuum pumps, you want to size it properly. I think pretty much for the most part, as I travel throughout the nation and in Canada, I typically see around 7 CFMs. If you have something that's 10 CFMs, it will cover about 90-some% of everything that's out there. But the rule is pump size squared, okay? For example, 3 CFM pump equals a 9-ton system or less, okay? A 5 CSM equals up to 10 tons, all right? So keep a vacuum pump, but more importantly than the size of the pump, what I wanted to tell you is the oil. The oil has to be changed on a regular basis. It has to be changed, in my opinion, every time you do a vacuum down. Most importantly, you need to know the system. In some systems that are very, very wet, you might have to pump it down twice, okay? So don't be like, I'll just say me, don't be like Don and only change your oil when it tips over in your truck, okay? Or when it gets milky white. Obviously, I'm joking, but don't be that guy. And then I usually ask the class, how many people are using compound gauges, mercury gauges, your refrigerant gauges to pull down? Well, unfortunately, it doesn't work properly, okay? It does not work properly. It's too small of gauges. The 1/4-inch hoses are not meant, so it really doesn't matter what size of CFM you have as a vacuum pump, because the 1/4-inch gauges are only going to allow you so much to pull down, okay? So get the proper gauges that are rated for vacuum, okay? And you want to remove your Schraders to get that pulled down all the way, okay, with like a core remover. Obviously, it needs to be calibrated, a calibrated Micron gauge. And then we want to do a standing vacuum test, pardon me. And that's going to depend on the size of the system, all right? So that's going to vary a little bit. I know on a typical residential system, I would typically, when I first got started in the industry, I would pull it down and let it stand for like 45 minutes or an hour. Just enough time to maybe clean the job site up or go to lunch or something like that, or take lunch there in the truck. And then we need to prepare the system to receive our charge, okay? A couple things about vacuum pumps. It states using a 2-stage pump. I think for the most part, everything out there today is 2-stage, maybe not, but for the most part, let's just assume it is. We want to perform a blank off. And a blank off is nothing more than a fancy way of saying you're going to hook your Micron gauge directly up to your vacuum pump and pull it down to 500 microns to prove that your vacuum pump will pull down to that. Emerson's going to ask you to pull down to 500 microns or less, okay? I know a lot of guys nowadays are pulling down 200-300 microns. It's a different world out there. We were always told if you pulled it down too low, you'd break the oil down, but that's just a myth. It's not the case at all. So, and it was funny, I was telling the class not too long ago on this, about 2 months ago, and a guy started laughing in the front row, and he raised his hand and he said, I'm guilty of that. He thought it was his Micron gauges, and here he found out it was his pump wasn't even pulling down. So make sure, do you need to do it every day? No. Do you need to do it every week? Probably not every month, but you want to check it periodically to make sure that your vacuum pump can pull down to 500 microns. And then also, we want to use the ballast. And the ballast is what you open up on the top of the vacuum pump. A lot of guys don't know what the ballast is used for. And what you're doing there is you're opening up your ballast, and the vapor that's coming out of there is that moisture that you're pulling out of there into a vapor. You're lowering that pump down into a different vacuum, or those lines, pardon me, and it's boiling water at a different temperature, or a different pressure, if you will, okay? And it's coming out of that at the ballast. So really, when you open the ballast, all you're really doing is removing moisture. You're bypassing the oil and removing that moisture out into the air past the oil. It'll help you keep your oil a lot better for a lot longer time, okay? Once the Micron gauge hits somewhere around 10 to 15K, thousand, on the microns, you're going to want to shut the micron or the ballast off, okay? And I did a lot of research on this a couple summers ago. Depending on the manufacturer, it's going to be somewhere between 10 or 15,000 microns. Start to shut that ballast down and pull down. Close the ballast and pull down. We want you to monitor the pull down activity, okay? Now, when you go to pump down, remember, if you have your Micron gauges sitting right next to your vacuum pump and you pull it down to 500 microns and say, that's good, I'm there, you're going to be fooling yourself, because at the end of that system near the evaporator, especially if it's a really long line set, it's not going to be 500 microns. So location, location, location is going to be important. Where you have your rig at and you're putting your Micron gauges on it, you want to make sure you keep your Micron gauges clean. So you want to put it in a port where it's not getting oil through it all the time. If for some reason you should get oil in your Micron gauge, there is things you can buy, obviously, but rubbing alcohol works real well, I found, okay? But be very, very careful on that, all right? This is a neat slide. It's just showing you, if you're pulling down with a compound gauge or refrigerant gauges, what your accuracy is. I didn't know this before I got here, but between every hash marks, we all know that it's 2 inches of mercury. What I didn't know is that 2 inches of mercury between those hash marks is the equivalent of 50,800 microns. Now think about that. We just said we wanted 500 microns, and between that hash mark is 50,800 microns. That's a big difference. I mean, close doesn't count. So on a very hot day, okay, and you're working hard and you're behind on your calls and you're trying to pull down there and you're in a hurry, okay, just between those two hash marks is what, 25.4, right? So close doesn't count. How many of us have gotten calls saying, are you about done out there? I know I had many a times. I used to hear it in my sleep. You've got another call to go to. So use calibrated gauges, okay? And how do we know we have calibrated gauges? When we do our refrigerant charge, for example, when we're recharging. I'll hold that thought here right now. We'll talk about that a little bit later then. So we want to use a calibrated Micron gauge, okay? Now look at this chart here. On the left-hand side, again, we want to remove the Schrader cores. We want to use the proper hoses, okay? You can see the proper hoses. This is a unit that we pulled down in Sydney, okay? This is a very small unit. It was a P-TEC unit, so it's going to pull down very quick. But the idea is just to show you what we did here. Obviously, we have our vacuum pump here. We have our rig set up there, okay, on our T. We've got our core remover. We've got our hoses here. And off to the side where you can't see it is the front of our Micron gauge, okay? And we said, again, that we want to pull down to 500 microns. You can see my core remover. I took a picture of this in my office here. You really, really want to have two core removers. It's so nice. It makes life so much easier. So on this chart over here, what we did is this is the face of the Micron gauge, and we were pulling down so quick trying to get to 500 microns. By the time we took the picture, it was 485, okay? On the left-hand side, we have microns. On the bottom, we're just showing minutes. It's not really about time so much as it is microns, okay? If you're down to 500 microns, we know we have a tight and a dry system. If you're above, let's say, 1,000 microns, the vacuum might be tight, but you still have moisture in that system. So be aware of that, okay? This just shows you a little chart on microns. At atmospheric pressure, face of the Earth, we have 760,000 microns. Our gauges are zeroed out at atmospheric pressure. We boil the water, again, at 2012. I'm going to come down here to 50,000 because we just showed those mercury gauges, equivalents. Look how we're close, it's 27.95, and that's 50,000 microns. We're boiling water at 101, okay? So if we go back here, at 500 microns, it's not going to pull up for me. We're close to 30 on our gauges. We're boiling water at a -12, okay, over here. And that's that's what we want to be at, 50 or 500 microns, okay? We're boiling water at -12. And I'm sorry that slide wouldn't pull it. I noticed earlier that nothing's moving on here. I usually bring arrows in and things, and it's not working, so just bear with me here a little bit. So we're going to talk about refrigerant charging. So we did everything we just talked about. We've got a system here. We haven't released the refrigerant yet. We brazed everything in. Our condenser, our outside condenser, we're going to keep this very simple, is a basic air conditioner. So we have a service port here, a service port here, okay? We did our calculation on our line set, and we came up to the calculation that by our calculation of the length of the line set, we're going to have to add another 4 pounds, we'll say, okay? So we're going to add our refrigerant to start with in our liquid line, and we're going to assume that it's a blend, and we're going to turn the tank upside down on a scale, okay, and start with the system off, start charging the system. We get almost all of it in. Let's say we get 3.5 pounds in just for the heck of it, and we really want to be accurate. We want to get that last half a pound in there. We would then open our ports up, obviously, start the system, let it stabilize, and then we're going to connect our system, our tank of gas right here in the suction. Obviously, we can't put it in the liquid line. The pressure would be too high. But then again, we want to be careful here, okay, be putting liquid into our vapor pump, right? Or we'll hear those crunchy noises. I always use the term goose it a little bit. A little bit will go a long way. Let it stabilize. Let your gauges stabilize to see what you did. They've also got those little vapor converters that you can hook on there. Those are really nice. That changes that over to quicker for you from liquid to the vapor. Okay, almost like a piston device. We start the system up. So just to recap on that, best practices, we put in the initial charge, liquid on the high side. If it's a single component, we're topping off the charge in a vapor on the low side. We always remove our blends from the cylinder as a liquid. We don't want to cause any separation or fractionization, okay, and that's what you're going to get with a blend, okay? We're going to use charging charts, our PT charts. We're always going to weigh in. We're always going to weigh out. And then last but not least, my favorite, verify airflow across the evaporator. Airflow, airflow, airflow. If you've ever been in one of my classes, you're probably giggling right now because I really hammer the airflow. If airflow's not right, nothing else will be, okay? So you have to have the airflow correctly, okay? And then it says verify superheat and subcooling. Let's talk about those two. I've got a shot here of just some compound gauges, and I usually ask the class, what's wrong with this system? And the answer is we don't know, because we don't know what application is, and we don't know what refrigerant we're using. What I'm going to suggest to you, this slide is telling us today, because I'm not doing it in front of you, okay, it's not instructor-led, it's over the internet, is if you're living in a pressure world, get out of it. Start living in a temperature world. Temperatures start everything, okay? The temperature outside causes my pressure to rise, right? The ambient temperature outside, and so on and so forth. The temperature outside causes my pressures to go up on my condenser, right? So, and we only use our gauges outside of the condenser. We use the law of physics to read the temperature from our evaporator outside, okay? We can't take the door off the evaporator and stick our temperature probe inside the evaporator to see what the temperature is. So again, we use the law of physics to take our pressures to get our temperatures, but it all starts out with a temperature. To prove that, if I start my sprinkler up outside, my pressures will change if I'm using my sprinkler around that compressor. But temperatures start everything, okay? You can walk into a walk-in cooler, if you're in refrigeration, that box might be always 30. I'm just going to throw a number out here, or 25, or whatever that looks like, whether it's medium or low temp, okay? But the refrigerant pressures might be different depending on what refrigerant they're using. For you residential guys and gals, you can have two houses side by side, same application, same load on the houses, same amount of people. One has 410A, one has R22. I can assure you that that coil is somewhere between 40 to 45 degree temperature, somewhere thereabouts, okay? But the pressures are going to be totally different. So don't get hooked on pressures, okay? Know the science of the temperatures. This is just our PT Pro. I wanted to kind of promote a little bit and just to show you. So what they're saying here is 410A at 100 PSIG. We would put it in our PT Pro here, or go to your PT chart. When we hit the done button or finished or enter, the saturation temperature would then become 31.5. That is the actual temperature inside our evaporator. When we're talking about superheat, we're talking about the temperature that's in the evaporator subtracted from what's leaving the evaporator. When we're talking about subcooling, we're talking about the temperature of the refrigerant inside the condenser versus the subtracted the temperature leaving the condenser. That's how simple that is. If we wanted to go farther, we had 31.5 here. If we took our temperature at our bulb leaving the evaporator, that bulb from our TXV, and we put 41.5 here, the difference would be 10 degrees superheat, okay? So we got three different states of refrigerant here. We have saturated, which is vapor and liquid. We have subcooled, which is liquid, only found in the liquid line. It is a refrigerant that's in liquid form. It's below its boiling point. So in that graph I showed you earlier, if the water is 211, that is technically a subcooled liquid at 211, even though it's hot. Superheat is the heat added to a vapor, that 213 we talked about, okay? That is superheat. Superheat, we need to know, is always a vapor. If you're looking anywhere else but the suction line, you're doing it wrong. If you're looking anywhere else but the liquid line for subcooled, you're doing it wrong. My question usually to the class is, what moves heat better, liquid or vapor? And the answer is liquid. Liquid is a better heat transfer. It transfers heat better. And if you ever, usually I get about 50-50 split or 64 split, and I always use an analogy that I learned from another instructor years ago is, think about it. If you could live outside with 60-degree temperature outside, could you survive for 24 hours? And the answer is yes. Could you survive in 60-degree water with it up to your neck, whether it's a swimming pool or a lake or whatever? And the answer is no, because it would remove the heat from your body so fast. Depending on your body mass, you might last minutes, you might last hours, but you wouldn't last 24 hours. So liquid is the answer of a better transfer, okay? Here we're taking saturated refrigerant. We're taking our pressure here. You can see we've tried to make this look like saturation. We've got bubbles in there. We're taking our temperature. Emerson's going to ask you, when possible, take your temperature from your pressure within 6 inches of each other. So I've got my fancy probe on here. I've got 115 degrees. I've got 290. Looks like we're using 404 as a refrigerant. When we went and took our PT chart, it said 115 on it. The moral of the story is that refrigerant is, in fact, saturated, okay? So all we're doing is going to our PT chart. Our PT chart is saturated temperature. Those are the temperatures and pressures that's inside of our condenser and our evaporator, all right? Remember, dew point, what was dew point? Dew point is your vapor, and bubble point is your subcooling, right? So we want to take it within 6 inches. Where would we find this saturated refrigerant? Well, we'd find it in our coils, our condenser coil and our evaporator. This is also considered latent heat. We're changing state without changing the temperature. We're going from a liquid to a vapor here, and here we're going from a vapor to a liquid, or back to a liquid, okay? And if you haven't noticed by now, if you're new in the industry, the vapor on a condenser, at least the ones I've always seen, usually enter from the top because the liquid is heavier, obviously. So the vapor will enter into the coil from the top and turn into, as it rejects that heat, starts boiling off, it'll go into a liquid, okay? Subcooling. Subcooling, we need to know right away, is liquid, and we're going to find it in the liquid line. Again, we're going to take our temperature, our pressure here, our temperature reading, and within 6 inches on our liquid line for our subcooling, okay? What it's saying here is our liquid line was 107. Our PT chart said it was 113. The difference of what's in my condenser and what's leaving my condenser is 6 degrees. We therefore have 6 degrees of subcooling, okay? Where would we find subcooling? We'd find it here, okay? Now, I'm going to tell you that it's very important to take our subcool reading before our metering device, because if our subcooling's not right, our superheat won't be right. Remember this bulb over here? This bulb is reacting on heat or temperature. It's opening and closing depending on. So if it gets too hot, it's going to open up that diaphragm on the metering device and let more liquid refrigerant in, okay? So if you don't have a solid column of liquid here, you have an inefficient system, okay? I want to also take it back here, all right? I like taking it in both places. For one reason, in residential, you're going to have some place to take a pressure reading. And I said 6 inches earlier, in residential, it's not going to be realistic to be able to take a pressure reading. But I can tell you the difference is going to be minimal, okay? But if it's major, we want to start looking for maybe a kinked line set, okay? Or maybe somebody at 5 o'clock, beer 30, if you will, on a Friday, just took a piece of copper off their truck because they were missing a piece here and just cobbed in a small piece that wasn't right, going back to that restrictions like we talked about earlier. Okay, so take them in both places. We want to confirm that we've got liquid all the way to the metering device. Okay, so last but not least, we want to look at superheated refrigerant. Again, it's heat added to a vapor above its boiling point. All right, so we're going to be doing this in the suction line, obviously. And in this exercise, it's showing us that we've got 74 pressure, PSIG, on our line. We're also saying that our line temperature is 43 degrees. We took our PT chart, and if you go to your PT chart and look at the refrigerant here, 404A, you will find at 74 PSIG, the temperature of 404A should be 33 degrees. The difference between the 43 and the 33, what our line temperature leaving the condenser, the evaporator, and what's in the evaporator is 10. We therefore have 10 degrees superheat, right? Okay, so that's how we do superheat. Where are we going to find superheat? We're going to find it 2 places, okay? You can see everything that's red is superheated vapor. This is suction line, low pressure superheated vapor. This is our discharge line, high pressure superheated vapor. But we're only going to take the superheat in 2 places, and those 2 places are going to be here. And why would we take it there? Well, we take it there to make sure that our metering device, is matching our load, okay? It's doing what it's supposed to, all right? We want our superheat to be matching the load. Is the evaporator correctly? We also want to take a superheat reading before our compressor. Why would we want to take a superheat reading before our compressor? Okay, and you have to forgive me. I'm used to delivering this class live, and I like a lot of engagement. But we want to take a superheat reading there because we want to confirm that we only have vapor going into our vapor pump. If we don't have, even if it's only 5 degrees or 6 degrees or 10 degrees, we know we have something, okay? All right? But we want to prove that. I'm also going to ask you a little known fact here, or maybe a lot of you know this, is I want you to add this to your tool belt starting tomorrow. I want you to take a temperature reading right here, 6 inches down the discharge line, leaving the compressor. And the reason, we're not calculating superheat there, but we want to calculate the temperature 6 inches down, leaving the compressor on our discharge line. And the reason for that, we never want to be higher than 225. All of our semi-hermetic compressors are like that, and 98% of our scrolls, okay? And what they have found over the years testing compressors for overheated compressors is the hottest point inside a compressor, okay, inside the scroll set leaving there, we lose somewhere between 50 to 75 degrees heat, okay? We lose 50 to 75 degrees heat from the hottest point of our compressor to 6 inches down our discharge line. So if we lose 70, let's just say the worst scenario is 75 degrees. If we take that 75 degrees and we add it to that 225 degrees that we never want to be hotter than, we come up with the number or the temperature of 300 degrees. What's the significance of 300 degrees? The significance of the 300 degrees is oil starts to break down. So this is a nice way, because we can't stick a temperature probe inside the compressor, can we? This is a nice way with just taking temperature readings on how to tell what's going on inside your compressor, okay? Again, don't go any further than 6 inches. Take your temperature reading. Always make sure. Now, if it's above 225, let's say it's 235, does that mean the compressor's bad? Of course not. It just means we need to go back here and take our temperature reading. Maybe this is too hot. And then we're going to start backtracking. Maybe it's too hot. We may find right down here that this metering device isn't working right, and it's starving the evaporator, and our superheat's starting too early. So it's get hotter than it's supposed to before we ever get it. It's definitely running outside the envelope, and I can assure you that if it's 235 or 245, it definitely has a high compression ratio, which means nothing more than your discharge head pressure is too high and your suction pressure is too low, or both of them, okay? Very, very important. Real quick, I'm going to do compressor fundamentals more than likely a few weeks down the road, but to calculate compression ratio, you're simply taking your pressure readings off of your gauges at PSIG, and you're adding atmospheric pressure, which is 14.7, but for easy math, we add 15, okay? So in other words, if you had 185 on your high side and 5 on your low side, and you were at your atmospheric pressure rounded up to 15, you would have 200 and you would have 20. You would take that 20, divide it into the 200, and you should come up with a 10-to-1 compression ratio. And that's just an example. I just plucked those numbers and used them as an example. If you have a 10-to-1 compression ratio, that is a low refrigerant system. A 5-to-1 is usually a medium, okay? And a 3-to-1 is typically somewhere thereabouts is an air conditioning system, okay? It doesn't mean that it can't be 2.9-to-1. It just gives you a ballpark figure, okay? So to bring it to a head here, we said saturated refrigerant there, okay? We're changing state, which is latent. We're changing state but not changing temperature. We'll find that in our condensers coils and our evaporator coils. We're going to find superheated vapor here in our suction line and our discharge line. I want you to remember, like our ball diamond, remember this. This is low pressure superheated vapor in the suction line. It's low pressure, so put equal, it equals low pressure superheated vapor. On the discharge line, we're talking about high pressure superheated vapor. So there is a difference, okay? Think about that ball diamond we talked about earlier. And you'll have access to this, by the way, like they spoke to earlier. These will be archived for you to look up. And I apologize if I stumble too much. It's the first time I've ever delivered a presentation like this with on the internet with this many people. I'm much more comfortable delivering it to 50 or 100 people live in front of them. I like to engage. Remember, the liquid line is high pressure, subcooled liquid. In the liquid line, it is high pressure, subcooled liquid, okay? Remember that. So you're only looking for subcooling in our liquid line, okay? All right? Leaving the condenser. You're only filing our superheat in the suction line, all right? And I think that might be all that I have. What's the difference between sensible and latent heat? Well, these are questions I typically ask the class and then bring the answers in. Sensible heat, we can sense the difference. Latent, we can't, okay? We're boiling that water, okay? But until that water, but it's not changing temperature. We have a temperature probe in that water, and it just keeps staying at 212. When that water leaves, that last droplet of water leaves the pan on my stove, no matter how high I kick it up there, as long as there's water in there, it stays at 212. The second that droplet leaves and goes to a vapor, it goes to 213, okay? And it always confused me when we talk about evaporators. We're boiling off. What are we boiling off if we're boiling that pot of water? I had an interesting talk with another instructor, and his analogy, he said, always remember this. When we're boiling that water, what are we cooling? We're boiling off, but we're cooling. Well, in the case of a pot of water, what are we cooling? We're cooling the pot, okay? We're cooling the pot because the second that water leaves the pot, I'm going to be buying my wife a new pot, right? So the energy okay? We use the law of physics. The energy of the liquid is focused on the energy is changing from a liquid to vapor, okay? It's not until that last droplet of liquid leaves that pot that it starts to focus on the pan itself, all right? And that's all I've got. Hopefully I didn't talk too fast or too slow, and it came through all right. I'm not sure if there's any questions in the chat box. I want to thank all of you for coming out. Again, this is a first of many of our series that we're going to be doing. We're trying to, I know some of you are working from home. I talk to a lot of technicians throughout the week, all the time. I keep in touch with most of my students that if not all of them, whenever they reach out to me. If you should have a question, you can get back with what Kara told you earlier. You can also email me at don.gillis, Gillis, @emerson.com. I did want to share with you tomorrow, the course is going to be more for the refrigeration guys, the refrigeration guys, pardon me. Dustin Tillery, my partner as another instructor, is going to be going over the E2, the navigation, and going over that. And Dustin does a great job with the E2 product, and you're really, really going to enjoy it, okay? Thanks to all of you for tuning in. I'm not sure if there's any questions out there. If there is, I'm sure they'll get to me. I appreciate your time. And again, we'll talk tomorrow. Thanks, everybody. Be safe.
Hey, Don.
Yeah.
We did have one question that was asked live, and it was, ideally, what should the compression ratio be, and can a ratio be too low?
Yes, good question. So I don't have a lot of time, but compression ratio can be too low. In fact, it's more crucial. So we've always trained our whole life that keep your head pressure down, but not a lot of people tell you to keep your suction pressure up, or at least they didn't for me, okay? But if you're 2 pounds of suction pressure, and I'll get into this when we talk about compressor fundamentals. So first, to answer the first question is, the compression ratio ballpark for air conditioning is 3-to-1. For medium temp application, it's 5-to-1. For low temperature, it's 10-to-1, or somewhere thereabouts, okay? So again, all you're doing is taking your discharge pressure divided by your suction pressure. You're adding atmospheric pressure to PSIG, which turns it into PSIA, absolute, and you're dividing that, okay? So you can have it, obviously you can have it too high and you can have it too low, and you can have it both, okay, if it's too high and too low. So for example, if it's too high, you might have a matted condenser outside, okay? If it's too low, you might have a matted evaporator inside, okay? So a great question, but you always want to keep your suction pressure up, because suction pressure plays a bigger factor, more havoc on your efficiency of the compressor. Just a little bit of lower suction pressure is a lot of head pressure, okay? I think it's like 2 pounds, 2 pounds of suction pressure dropped, you lose about 1% of your capacity on a compressor. And it's a pretty good, I don't like rules of thumb, but that's a pretty good ballpark figure. Kara, thanks for the question, by the way. Hopefully that answered it. Anything else, Kara?
That was the only one, Don. Thank you.
Hey, thank you. Thanks for everybody for tuning in. I appreciate it. Thanks, Kara. Tomorrow, E2, remember.